the optical region in iron or in cold atoms and use servo controls to lock one of the comb lines to the sharp optical resonance. And then the laser repetition frequency becomes a known integer fraction of this optical reference frequency. So if you want to use a frequency comb to measure an unknown laser frequency, you superimpose the pulse strain and the unknown beam on a beam splitter, and you look with a photodetector for a beat node. And as you are close to a comb line, you get a low frequency beat node that tells you just how far are you from this nearest comb line. And so in this way one can measure the absolute frequency of light to very high precision. And all of this is of course classical language. Roy Glauber asked a good question. Yeah, what if you think in terms of photons? What correlations, what noise properties do we expect? This has not been explored yet. But so just to summarize, with the femtosecond laser frequency comb, we have a tool that behaves as if you had 100,000 or 1,000,000 ultra-stable lasers at once. It's a revolutionary optical wave meter. If you include nonlinear frequency conversion, you can now count optical frequencies from terahertz to the ultraviolet, clockwork for optical clocks. An optical frequency synthesizer, if you have a sharp frequency anywhere in the spectrum, you can synthesize sharp frequencies anywhere else. It's even of interest as an ultra-stable microwave source. For us, it's an enabling tool for fundamental measurements, but it's also an interesting tool for people in ultra-fast science, because a laser that can produce pulses of reproducible electric field can be used to produce, for instance, single extreme ultraviolet pulses with pulse durations of 80 attoseconds or so at the moment. The first laser frequency comb was based on a Motlop titanium sapphire laser, and it's now an antique. It was handed over to the Deutsches Museum, this technology museum in Munich. Most people prefer to use fiber lasers based on erbium-doped fibers, which give you all the advantages of a mature technology that has been developed for optical telecommunications. And one can go out and buy a complete system, the laser or the servo electronics, from a spin-off companies that two of my students have founded 9 years ago. And of course, developments continue. One intriguing development is to make miniaturized frequency comb generators. Kerry Verhala and Tobias Kippenberg have long worked with microfabricated whispering gallery modes. You have a silica disk on a stem of silicon. You take a CO2 laser to melt the rim of this disk, so you have a very good optical surface finish, and you can couple light waves in there from a fiber in close proximity, and the cavity finesse or cube can be so large that you really get large powers circulating inside this very microscopic cavity, and as a result one observes a frequency comb at the output. The mechanism is not really understood in complete detail, but it's some kind of parametric oscillator pumped by 2 photons, so it's a 4-wave mixing process. And experimentally it has been confirmed that the spacing of these comb lines is uniform to 17 decimal digits. And recently it has been possible to generate octave spanning combs so that one can use this trick of finding the exact position of the comb lines. By now there are quite a few different approaches to comb generation using miniaturized cavities. For instance, at Cornell in the group of Gaeta, combs that are almost octave spanning have been produced with microfabricated silicon nitride toroids on a chip, and you can feed in the light with a waveguide that is fabricated on the same chip, so it's mechanically stable. Other comb generators have been based on crystal cavities fabricated the conventional way. On a watchmaker's lathe, you can grind and polish some crystal such as calcium fluoride or magnesium fluoride and make micro cavities that also act as comb generators. And these crystals have the property that you can make comb generators in the mid-infrared, which is of interest as a fingerprint region for molecular spectroscopy. So these are emerging technologies that one day may become available. But what is intriguing is that this tool, which originally was conceived as an exotic tool for those few people who are interested in making extremely precise spectroscopic measurements, that has begun to evolve in unforeseen directions, and there are more and more applications emerging that I find quite interesting. And I don't have really time to talk about everything that has been tried so far, but let's look at this evolutionary tree and look at a few examples. So the original application, of course, was optical frequency measurements. And actually the poster that was printed on the occasion of the 2005 Nobel Prize illustrated how you would use a frequency comb to measure resonance frequencies in the simple hydrogen atom. And that has been something that our team has been pursuing now altogether for 40 years, to look at the simplest of the atoms, make very precise measurements, and see if we find a contradiction, if maybe we reach the limits of current quantum mechanics theory. But so to measure such a frequency, you take a laser, you send it to the atoms to see if they get excited, and then you send another part of that beam to the frequency core to find out just what is this frequency. The actual laboratory setup looks slightly more complicated. This is a setup where many students have received PhD degrees, a hydrogen atomic beam apparatus, and some laser sources on the table behind. And hydrogen, of course, has been the Rosetta Stone that has made it possible to decipher the strange rules of quantum physics. It has inspired many path-breaking discoveries, from Balmer and Bohr and the old quantum physics to wave mechanics, to de Broglie and Schrödinger, onto relativistic quantum mechanics and onto quantum field theories with the discovery of the lampshift. And in our work, we've long concentrated on one particularly sharp transition in hydrogen, a two-photon transition from the ground state to the long-lived metastable 2s state. You can excite it with ultraviolet light at 243 nanometers. Two counter-propagating beams will excite this transition free of first-order Doppler broadening, and the natural line width expected is only about 1.3 hertz compared to an optical frequency of 10 to the 15 hertz. The observed lines are not quite yet at 1 hertz, but they are sharp, a few hundred hertz. And just to see what that means, if you take the visible Balmer spectrum that we looked at a moment ago and stretched it so that it fits on the same scale, you could wrap it around the globe, and not only once, but about 20,000 times at that scale. And so such a sharp line allows precise frequency measurements, and we actually made two such measurements in the past. The very first one in June of 1999, the first measurement with a laser frequency comb, and we were very proud that we reached an uncertainty of 1.9 times 10 to the minus 14, which was an order of magnitude better than anything people had achieved before with these large harmonic frequency chains. And we made a second measurement in February of 2003, which agreed, not with the big improvement in accuracy that we had hoped for, but the fact that it agreed was a disappointment to at least one theorist, Harald Fritsch, who had called every day during 2003 to get a preliminary result, because he had predicted that we would